I'm Congyao Zhang, and today I'm going to talk about runaway merger shocks in galaxy clusters. And my main collaborators in this project are listed here. So I will start my talk from mergers of galaxy clusters. They are essential for the cluster growth. You may have seen this beautiful image many times, which shows one of the most famous examples of merging clusters, the bullet cluster. The red and the blue colors show you the distributions of the hot gas and dark matter. I think one basic but very important fact about cluster mergers is that they are always supersonic. It's just because the cluster free fall velocity is always comparable or larger than the sound speed of the intercluster medium. So that's why during the merger process, merger shocks are naturally formed. So again, in the bullet cluster, we can clearly see the merger shock front here in the X-ray image. In the right panel, I show you the gas profiles measured along the horizontal direction. You can see the shock front is here, and there is another edge which corresponds to a contact discontinuity. It's also known as the cold front here, which separates the gas halos of two merging clusters. I think the biggest difference between the cold front and the shock front is that at the cold front, the pressure is continuous, but it is not at the shock front. And in this slide, I'll show you a movie of a merger between two idealized galaxy clusters to show you how the cold front and shock front form during the merger process. And here, idealized cluster means each cluster is composed of spherical dark matter and gas halos. They are both in equilibrium in each conditions. You can see in this movie, the left panel shows you the modeled X-ray image, and the right panel shows you the temperature distribution. So from the start of the simulation, you can see there's a small subcluster enters into the main cluster from the top left. And the gas field of the main cluster is significantly disturbed by this infalling subcluster. And this entire system spent a few giga-years to recover its visualization. 4 snapshots from the previous movie are highlighted here. The black dashed line shows you the trajectory of the infalling subcluster, and the black arrows mark the position of merger shocks. The boundary between the gas halo of the subcluster and the atmosphere of the main cluster is a cold front. So you can see in the first and the second panels, the cold front and shock front move together along the same direction. However, after the pericentric passage, the subcluster starts to decelerate, and it eventually falls backward after crossing the epicenter. But in the meanwhile, the merger shock all the way moved to larger cluster radii. So you can see in the third and fourth panels, the distance between the cold front and shock front becomes larger and larger. And in this process, the merger shock experiences a transition from a bow shock to a runaway shock. And for this reason, we summarize the formation and evolution of merger shocks as a two-phase process, the join phase and the detach phase. An important point here is that in the detach phase, the subcluster has only limited impact on the runaway shock, whose propagation is mainly determined by the surrounding atmosphere. And more interestingly, while moving down a steep gas density gradient, the runaway shocks could be long-lived. Here, we used simple 1D simulations to illustrate this point, and where we assume the initial gas density profile of the atmosphere follows a power law where omega is the index. And this right panel shows the curves in this right panel show you the evolution of the shock strengths when the shocks propagating in the atmospheres with different omega. So you can see generally when omega is larger than roughly 3, the shocks could maintain their strength over a large distance. So here, I think a natural follow-up question is how steep the gas density profiles are in real galaxy clusters. In this figure, I show you the logarithmic slope of gas density profiles of galaxy clusters measured in X-ray observations. And the solid lines show you the results of 12 galaxy clusters presented in Reclini 2006. And the curve for the Abel 133 is highlighted in red with error bars which is measured from much deeper tangent observation. So generally, beyond R500, we can see the gas density profiles could be as deep as R2-3, and these observational results suggest that there is a habitable zone populated by runaway merger shocks outside R500. And here I have to emphasize that to identify these runaway shocks in the habitable zone in the current X-ray observations will be difficult because the gas density is low in this region. So either we need more advanced X-ray telescopes like Stina or Lynx, or we need the help of other wavelength observations like the radio observations. We know that in emerging clusters, merger shocks sometimes associate with the radio relics found in galaxy clusters. Here in this left panel, I show you our modeled synchronous radiation from the runaway shocks. The different curves show you the radiation at different wavelengths. So you can see the key feature is that the strong radio emission from runaway shock is always confined to a narrow region shell, radial shell just behind the shock front here. And this feature is generally consistent with the geometry of the radio relics found in class outskirts. For example, in this right figure, I show you an observation presented in Xiaoyuan's new paper, where the white contours show you the radio relics identified in this cluster near the virial radius. Now I think one may ask, on the left side, it shows the runaway shock in the theoretical model, and on the right side, it shows the radio relics in the observations. So can we really connect these two things? Maybe we can. Here in this figure, I show you the X-ray image of coma cluster overlaid with WSRT radio contours. And there is an enfolding group NGC 4839. We carefully modeled this system with our cluster merger simulations, showing the right panels. This is modeled X-ray and the temperature distributions. So you can see in morphology, our model provides a good match to the observations. And in our model, the group is close to its epicenter. And the merger shock, marked by the right dashed line, has detached from this subcluster. And you can see in position, this runaway shock coincides with the radio relic in the coma cluster. So for this reason, we believe that in the coma cluster, a runaway shock driven by NGC 4839 is moving somewhere here, associated with the radio emissions here. And more interestingly, in our simulations, we found that in the detached phase, actually, well-developed merger shock shows an N-shaped waveform. The aforementioned runaway merger shock is actually just the leading edge of this N wave. There is another trailing edge, which is closer to the class center. And the typical distance between the trailing and the leading edges could be up to Mach parsec scale. Here, this right panel illustrates how the N wave is formed in galaxy clusters. When a shock becomes weaker, a rarefaction emerges, and because of the stratification and the non-linearity, this rarefaction becomes sharper and sharper, and eventually becomes a secondary shock front of the N wave. So you can see this N-shaped wave. That's why it's called the N wave. And in our cluster merger simulations, the runaway merger shock, say the leading edge of the N wave, is marked by the red arrows, and the trailing edges are indicated by the black arrows. And if we go back to the coma cluster, this is our model. The runaway shock is here, and the trailing edge of the N wave is marked by the black arrow. And in observations, such a shock has been identified in the Planck SA image at 2013. So at that time, no one really realized there is a connection between this shock and the radio relic in the cluster, at large cluster radius. So I think the most interesting point here is that the radio relic in cluster outskirts and the shocks in the central region of cluster, and also the enfolding subcluster, these three stuffs Mach per cycle away from each other, but they actually have the same origin. They are all natural outcome of a single merger event. So if you are interested in the formation of N waves in merging clusters, please check our new paper, which was posted on arXiv yesterday. And this is still not the end of the story. In the next few gigayears, these runaway merger shocks would continuously move in the coma cluster outskirts until it encounters the accretion shock. And we know that at the boundary of the intercluster medium, there is an accretion shock which separates the hot SEM and the cold IgM. And generally, when the runaway shock collides to the accretion shock, three discontinuities are formed: a forward shock, a reverse shock or rarefaction, and also a contact discontinuity in the middle. And in this problem, the forward shock is particularly interesting. We call it merger accelerated accretion shock, the MA shock. MA shock is interesting because it's powered by merger rather than the accretion. But at the same time, the MA shock could have very high Mach number. The Mach number of MA shock is approximately the product of Mach numbers of two merging clusters, which means the typical Mach number of MA shock is up to a few tens to a few hundreds. Here we use 1D cosmological simulations to illustrate the formation of MA shocks. And this figure shows an example of our 1D simulations. The x-axis shows you the cosmic time, and the y-axis shows you the radius. The color represents the gas density. So you can see at the beginning, an ordinary accretion shock is formed here, and we initiate a secondary shock at t equals 2.5 gigayear to mimic the runaway shock. And the secondary shock quickly catches up with the accretion shock at this point, and after that, MA shock is formed. You can also see the contact discontinuity formed there. You can see after the shock collision, the SEM of this cluster is significantly expanded by a factor of up to a few. And actually, in our simulations, we found that the evolution of MA shocks depends on mainly two parameters. One is the Mach number of runaway shocks. The other is the cluster mass accretion rate. So generally, most of the MA shocks could survive for a few gigayear in galaxy clusters, which means for most of the strong shocks we observed at the boundary of galaxy clusters are actually the MA shocks rather than the ordinary accretion shock. Another interesting feature I want to highlight in this talk is that after the shock collision, there is a high entropy shell formed between the MA shock front and the contact discontinuity in this region. So you can see in our 1D simulation, the high entropy shell is here, and also such a shell could be seen in the full 3D cosmological simulations. So you can see in this figure, the black solid lines show you the MA shock front identified along the non-filamentary directions. And this high entropy shell could further excite hydrodynamic instabilities in the cluster outskirts and may further contribute significant non-thermal pressure in this region. And in my last slide, I want to briefly introduce Stephen Walker's new paper, where they identify two giant contact discontinuity in the outskirts of the Perseus cluster, here and here, and near the virial radius. So we argue that this outer edge could be explained as the contact discontinuity formed in the collision between the runaway and the accretion shocks. As a comparison, I show one of our simulation here. This figure shows the evolution of gas entropy. So you can see the contact discontinuity formed in the shock collision is here. There are two interesting points make our scenario attractive. One is that both of these two edges are mostly tangential to the cluster radial direction. So here, for a more clear view, I overlay two circles here. And another interesting feature is that outer edge is close to the Perseus virial radius. Actually, these 2 points are both natural outcome of our shock collision scenario. And this is the explanation for the outer edge. The inner edge is could be either a rarefaction formed in the Shock-accretion, or it could be another contact discontinuity formed in the past merger event. So I think I will stop here and leave my conclusions in this page. Thank you for your attention. I'm happy to answer your questions.
Thank you very much. So we have time for a couple of questions. Let's see, the first one is from Craig Heinke, who asks, in the coma cluster, is NG4789, which appears to have strong radio emission, is that associated with the radio relic, or is the group only accidentally imposed on the particular features that you're looking at?
I think here, this is a radio relic, right? But there's, I think for this.
Sorry, just to be clear, be clear, he was talking about NGC 4789, so that's the one just below the.
Okay, this one.
Nope, the other one, to the right, just below the radio relic.
Just okay. That's this one. Okay, I see. Yes, I think at least in our model, we need the mechanism of radio emission is the pre-existing relativistic electrons was accelerated by the runaway shock. So actually, we need two things. One is the runaway shock. The other is pre-existing relativistic population of the electrons. So I think one explanation of where is the electrons coming from is from some radio galaxies, maybe from NGC 4789, because in spatial they are associated. But I think it's hard to really confirm this point.
Right. Great. And so time for one more question from Daniel Wang. He says, nice talk. What is the highest speed that the runaway shock can typically achieve, and how much energy can be deposited in the outer regions of clusters, and how far can the shock get beyond the virial radius?
I think the typical Mach number is runaway shock is 2 to 3, because I have argued that if the omega is steeper, roughly 3 or 4, the shock could maintain their strength. So for a typical Mach number of the merger shock is roughly 2, 3, or 4. So that means a typical Mach number of runaway shock in the class outskirts could be at the same level. And it will all the way move to large class radii, which means it could reach very large class radius and encounter the accretion shock. So which means like in our 1D simulation, for example, here, the dashed line and dotted line show the virial radius of this cluster. So you can see actually the MA shock could reach 2 or 3 times the virial radius.